Today we're going to talk about experimentation and reasoning. So the topic I've prepared for today, is a bit different from the usual, statistical topics we had based on statistical learning. Today we're going to talk about A/B testing and then quantitative reasoning under incomplete information or with no information. So first, let's start with A/B testing. So this is a type of experimentation. So with A/B testing, the idea is that we want to, set up a very simple experiment to measure difference between two groups. So in a sense, this is somewhat similar to two-sample t-test that we discussed last week. So for example, we may have two different website designs, and we're interested in click rate, in conversion rate, or the fraction of times that users who land on this page click on the Learn More link. So there are two options, having that link in blue or in green. So for measuring the difference between the conversion rate under design A and under design B, we need to have two groups. So we have group A, users who are exposed to the blue button, and group B, users who are exposed to the green button. And then we measure how many of those users click on this link. So let's say for the blue link is 52, and for the green link is 72. So can we say that the design of the link, the color of the link impacts the conversion rate here, given that these two numbers are not equal? How can we do that? Well, one very naive idea is just looking at the numbers, right? They are like 20, they have a difference of 20%. Is this difference sufficient? So the thing is, we need some basic, experimentation set up to be able to claim with statistical significance whether, the color of, changing the color, let's say from blue to green, makes an impact on the conversion rate. So conversion rate is the fraction of people who click on the link. So there could be other examples. For example, if we're measuring the impact of some treatment, we have like some control group who received the placebo and a treatment group who received the drug, and then we measure something between those two groups, just like the example from last week. Or sometimes we have some current design, some existing design maybe, and we want to check whether by making some change we can improve something, right? Then that current setup is group A essentially, and that variation is group B. So another example is let's say two different ads, right? We have two different designs for some online ad, and we want to see which thumbnail, which colors, which headline leads to higher conversion rate. So the thing is, especially with online services, it's very easy to set up a simple A/B test or A/B experiment. So the way we can do it is by just distributing the incoming traffic of users into two groups, right? So randomly, we either show them, type A ad or type B ad, and then measure their behavior based on, cookies and other, ways that we can track users. So, so here are, some other examples where, A/B testing could be relevant. So there are, in general, parametric tests and non-parametric tests, and we're going to only discuss one non-parametric test today, which is permutation test, based on what we discussed last week. So with permutation test, the idea is that we measure that outcome of interest, for example, conversion rate in group A and group B. Then we need to just permute or shuffle the cases, shuffle the users, and pretend that now they belong to a different group A and group B, just like permutation test from last week. And then based on that resampling, we measure the outcome of interest again. And we just repeat this process many times, maybe 1,000 times, to get the histogram of the outcome of interest under permutation. And then based on how extreme the actual observed value is compared to the null distribution, or the distribution of the permuted measure of interest under the null hypothesis, based on that, we decide whether to reject the null hypothesis or not reject the null hypothesis. So the results here can be interpreted as causal, because we are indeed perturbing the system, and if we set up the experiment properly so that there is no other difference between group A and group B, and they are randomly assigned to the two groups, then the result can be interpreted as causal. So for example, if we say, all right, let's first collect the data for group A, let's just have the design with the blue button for 1 hour, and then after an hour, we have sufficient data for group A, then we change the design to group B, and those users will be group B. Do you think this setup would be suitable? What do you think?
Maybe there is some other than the control volume, there's something different other than control, like the time?
Yeah, like the time. So if we do something like that, the experiment is not designed properly because group A are also people who went to our website maybe earlier in the morning. Therefore, their behavior is also impacted by time. And then group B are people who check the website later in the day or at some other time. Therefore, we cannot be sure if there is a difference. We cannot be sure if that difference is a result of our perturbation, if it is a result of color of the ad. So some success stories about A/B testing. So large tech companies like Microsoft and Amazon have used A/B testing for many different ideas. So one general statistic is that around 10% of A/B tests in these tech companies result to some positive results in terms of being able to detect some difference in the outcome of interest. So there could be many ideas that people in these companies have for improving, for let's say increasing their revenue or improving the user experience or some outcome of interest. And based on this simple test, they have observed that 10% of these ideas are proven to be relevant. And given how easy it is to run these experiments, it makes them very important. So for example, in Microsoft, apparently they were considering changing how ads are shown on Bing search websites. And they run some A/B tests on different ways of showing ads on Bing search results. And this led to a 12% increase in Bing ad revenue. And that means an additional revenue of around $100 million per year. So just such a simple idea could boost revenue by hundreds of millions of dollars for such large companies. So in case of Amazon, they had apparently some time ago they had ads for credit card on their landing page, on their homepage. But then they were considering whether to move these credit card ads to the checkout web page. When someone has already selected some product, it's in their cart, and they want to check out, and then in that checkout page they can advertise that credit card differently, maybe saying apply for this credit card and pay nothing for this item, right? So the thing is, when someone has already selected an item, this is just speculative now before the design. When someone has, let's say, selected an item that is $500 and it's in their cart and they want to buy it, they want to check it out. So the value of that item for that person is probably more than $500. That's why they are buying it, right? And the thing is, some of these credit cards have some, sign-up bonuses. So let's say some credit card with a sign-up bonus of $500. The thing is, when you represent it when you show it on that web page, then just with some speculation, it makes sense that the user would be more inclined to apply for that credit card because the bonus is just not some number, it's just not some 500 thing that appears on some account, but the bonus is that this thing that they wanted to buy becomes free. And probably the value of that item for them is more than $500. So, with testing, the idea is that we test, ideas for which there is some intuition, right? Because if we just, test random ideas again and again and again, because of false positive rates, some of our discoveries are just incorrect, right? So it makes sense to try ideas for which we already have some intuition that they could work. So in this case of moving credit card offer from the homepage to the checkout page, this boosted profit of Amazon by tens of millions of dollars per year. So again, another success story with A/B testing and just a very simple idea. Of course, there are also many ideas that they tested and they didn't observe statistical, support for a difference, for an improvement. So they are very easy to run. We just randomly redirect 50% of the incoming traffic to design A and 50% to design B. And this should be totally random, meaning that one person who goes to this website should have equal chance of being assigned to these two groups. And then we record their behavior. So let's see how we can implement this. So let's say that we have 20 subjects. So there are a total of 20 subjects on, let's say, some in the case of clicking on these ads, right? So from these 20 subjects, we're going to first randomize them so that we don't just show type A ad to the first 10 and type B to the second 10 people. So we randomize them. This is the same 20 subjects but randomized. And then we expose them to these two designs. So we expose the first group to design A and expose the second group to design B. And then we observe their behavior. So let's say this very first person, this one here, is shown design A and they do not click on the ad. So that's why I've shown that subject in red. The second subject, this person, the second person in the randomized list is shown ad type A and they click on the ad. So I've colored them as green. The third person also clicks on the ad. So we just continue observing and recording this behavior. It's just one of two possibilities because conversion rate is just a measure of fraction of people who clicked on an ad. So we just continue this. The fourth person didn't click, and these are the results. These are what we have observed in this experiment, right? So based on this, we can see that in group A, conversion rate is 40% because there are four green circles out of 10. And in group B, the conversion rate is 70%. So far, I think we didn't really use that much statistics. Then the measure of interest was the difference in conversion rate. So the observed measure of interest is just 30%, is the difference between B and A. So B minus A, the conversion rate in group B minus conversion rate in group A is 30%. So now the hypothesis test that we have is that this difference is sufficiently away from zero, right? So the null hypothesis is that B minus A is zero. And the alternative hypothesis can be something like B minus A does not equal zero. And that is B minus A in the population, something that we never have access to. So we want to be able to say something about the population based on this experiment with 20 subjects. All right, so then we're going to randomize the same 20 subjects again. So you can see that in total we had 11 green circles and 9 red circles. So they are represented here. So there were a total of 9 and a total of 11 people who clicked on the link. Now we're going to re-randomize. This is the part where we pretend that some random sample of these 20 people belong to resampled group A. The remaining 10 belong to resampled group B. So let's say these solid lines represent membership to group A for the resampling, and the dashed lines represent membership to group B. So now for group A, well, I have one person here who didn't click on the link, one person here, one person here, and one person here. So 5 out of 10 did not click, and another 5, which are here, 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 and here, these 5 clicked on the link. So conversion rate for this resampled group A is now 50%. And similarly, we measure the conversion rate for resampled group B. So I'm going to just use a different color. So in group B, we had this, right? These 4 people did not click on the link. Therefore, 6 people in group B, in resampled group B, these 6 people clicked on the link. Therefore, the conversion rate in resampled group B is 60%. This is just one reshuffling. And now the difference between these two resampled conversion rates is B minus A, which is 10%. So through this process, we want to say something about how extreme this value is. The thing is, when we just reshuffle the assignments and measure the outcome of interest under resampling, if these numbers that we get are very close to the observed value, this just means that the observed value is not an extreme, outcome. It is just some outcome that is expected by chance under the null hypothesis, under the hypothesis that there is no difference. But if we just repeat this process again and again, and we see that almost never we get 30%, then this means that 30% difference in conversion rate is some extreme value, and based on, the concept of p-value, which is probability of, observing a statistic equal or more extreme than the observed statistic under the null hypothesis, based on that p-value, which we get from this process, we can decide whether to reject the null hypothesis or not reject the null hypothesis. So we just measure how many times in our resampling we're going to get some conversion rates equal to 30% or more extreme than 30%. So if it is two-way testing, we just care about absolute value. So also negative 30% is also extreme. So now based on this resampling, this one resampling that we did gave us a resampling conversion rate of 10%. So this means that here we're going to just consider one unit. And then we try again, maybe we get now 20%. So we put 1 here. We just continue this process to make this histogram, right? So based on the observations, in each resampling, we're going to get some value. And just look at the distribution of these values. When we do, let's say, 100 or 1,000 resampling, we're going to get this blue curve. The blue curve is the null distribution, which means the distribution of the resampled outcome of interest under the null hypothesis. So under the null hypothesis, there is no difference. Therefore, we can just shuffle them and group them differently, right? Then and this is the observed value. The observed value was here, 30%, so it's this red line. And based on how extreme this red line is compared to this blue distribution, we decide to either reject the null hypothesis or fail to reject the null hypothesis. Any questions? All right, yeah. So let me show you p-value. So if on the y-axis we have density of this distribution, meaning that the area under the curve is 1. So this is indeed the case. So this is not just a histogram that represents frequencies, just raw frequencies. It's representing density. Then if h0 is b minus a, true b minus a, being equal to 0, and alternative hypothesis is this not being equal to 0. So for a test like this, the p-value would be this area plus this area. So these two together, they make up the p-value. So you can see that when these areas are small, it means that the red line is somewhat extreme, and it just means that observing that value under the null hypothesis is very unlikely. But we have observed it. So the reasonable thing to say is that it was unlikely to observe such a thing, but we observed it. So perhaps we need to go back and reject that assumption we made, which is h0 being true. Because in hypothesis testing, h0 represents our default state of belief. So the default state of belief in terms of these experimentations and trying these ideas is that the idea doesn't lead to a difference, right? And what we're looking for is sufficient evidence that allows us to change our default state of belief. So this was the example for p-value when the alternative hypothesis looks like this. In the case that we have a different test, let's say h0 is b minus a being equal to 0 in the population, and the alternative hypothesis being b minus a being positive. For a case like this, the p-value is going to be only this area will be the p-value, because we want b minus a. We want more extreme observation, right? So b minus a under resampling should be larger than the observed value. And the thing is, for experimentation, we need to decide about whether we're doing one-way test or two-way test in advance. We cannot just run the test and say, all right, we didn't find sufficient evidence for the for the two-way test. That's why we consider this as a one-way test. It doesn't work like that. So ideally, everything should be pre-registered before running the experiment. Any questions? All right. So this animation here shows A/B testing. So let's say the observed value is the black vertical line, and you can see that we're just resampling. We're just trying different permutations where we define resampled group A and resampled group B just randomly, and just obtain the histogram under the null hypothesis. This is the histogram. Here, the y-axis represents just raw frequencies. So this is not exactly the distribution function, but you can see that from this histogram, maybe we get some distribution function like something like this, for which the area under the curve is 1, right? It just comes from these frequencies. And then when we have this distribution, what we're going to do is looking at this area. Or in terms of the observation we had, this means that we're going to, if it is a one-way test, we're going to look at these frequencies. So I think this must be 1, right? So there's one observation of something more extreme than the observed value, 2 observations, 4, 5, 6, 7, 8. So we had 8 observations. I'm not sure what was the total. If the total was 200 permutations, this means that p-value is 4%. And as p-value is 4%, so number of permutations, let's say it was 200, and we observed 8 cases where we got something more extreme. That's why p-value is just number of times we get something more extreme over the total number of permutations, so it's 4%. Then if our tolerance for type 1 error is 5%, it means that we reject the null hypothesis. We reject the hypothesis that there is no difference. And this implies that changing, the design from, let's say, from A to B leads to a statistically significant increase in the outcome of interest. So you might be wondering where 8 came from. So this is 1, right? So I just counted how many times we got something more extreme. One time we got a value here, one time here, 2 times in this bin, one time here, 2 times, 1 time. When you add up these numbers, it's 8. So that's how the p-value is calculated. Questions? All right, so in permutation tests, one advantage is that we're not making any assumptions about the distribution. So in hypothesis testing with a theoretical null model, we need to work out what is that distribution under the null hypothesis. For example, for t-test, that distribution, if n is large, can be almost approximated with a normal distribution, right? For some other tests, we need, let's say, f distribution, t distribution, chi-squared distribution, right? But the thing is, with permutation tests, we don't need to worry about that part because we just run the experiment, obtain the histogram, just obtain the histogram and check how many times we got something more extreme. So we don't need to make any assumptions about the distribution. Yeah.
So the difference between this one and t-test use the standard deviation and the mean.
Yeah.
This one because we just counting the
Yeah.
number.
So we can also have A/B testing where we include something like standard deviation. But for this test, which was very basic thing, it was just whether people click on a link or don't click on a link. A simple test like this also works. But if we are testing some quantitative outcome that takes continuous values, then we also need the standard deviation. Yeah, and then there could be also more advanced A/B tests. But in many situations, we have some binary outcome, which is about whether whether some binary outcome of interest happens or doesn't happen. So this null distribution we generated under H0, so under the assumption that the two groups are not different. As we are working under that assumption, we can just relabel the subjects randomly. And the p-value measures the likelihood of observing the observed statistic or something more extreme under H0. This means that we have, under H0 means that we can just simply randomize the two labels, the labels representing whether one subject belongs to group A or to group B. So if p-value is smaller than the predefined significance threshold of like 5%, we reject the null hypothesis. Then depending on the test, we can have one-way or two-way test. These are testing different things with different interpretations. And as a sanity check for our experiment setup, before actually trying to measure anything, we need to run a number of AA tests. So AA test means that the two groups are exposed to exactly the same thing, right? So we do this just as a sanity check. So when we run AA tests, they should show no difference about 95% of time if our tolerance for type 1 error is 5%. So we run AA tests. How do we do that? Well, if it is the add-click problem, we just redirect the traffic into two groups, but then we show them the same thing. And then we measure their behavior, how many times they click on the ad and their difference, and do the resampling, the permutation and distribution, and calculate p-value and everything to see whether the null hypothesis gets rejected or we fail to reject it, right? Under that experiment setup, the positives, which means rejections, which means discoveries, should be less than 5%. Because all of them are false positives. Because it is AA test and there is no difference between the two groups. If our rejection rate, which is same as false positive rate here, is more than 5%, it means that there is something wrong. There is some difference between those two groups that we didn't include in our experiment setup. So this is just a sanity check, and after making sure that the AA we pass this sanity check, meaning that the false positive rate of AA test is less than 5%, we can then move on to actually perturbing the system and measuring the difference. So we can now try permutation tests in Jupyter exactly based on this example. Yeah. So this is not about rejecting null hypothesis anymore. With AA test, we know the ground truth. The ground truth is that H0 is true. So with AA test, the two groups are exposed to the same design. So it was about showing them a design like the one on the left with the blue button, or showing them a design on the right with the green button. But with AA test, we show them the same thing. We show the blue button to all users. Therefore, the conversion rate between the two groups should not be higher than our false positive rate. Sorry, than our tolerance for false positive error. Yeah. Yeah, so with AA tests, we just run, let's say, 1,000 AA tests, and some of those tests will be rejected, some of them will not be rejected. The fraction of tests that are rejected should be less than 5%. Yeah. This is some sort of simulation to just make sure that we're doing the experiment properly. Because there could be some factors that are not accounted for in the experiment, and they cause some differences between those two groups. And because of those factors, the behavior would be different. We want to make sure that there is no such factor. Maybe our randomization is not creating a completely random process. That's the issue. So it is tempting to just say, all right, let's first get the group A result and then group B result. But if we do something like that, one factor that is different between them is time. Group A were just exposed to the system earlier in time, right? So now let's just move on to Jupyter. Any questions before moving to Jupyter? No? All right. So all right, so you also have access to this code. This is from the GitHub page of Carlos Afonso. So here I'm just loading some libraries, as you can see. Here we're considering group A as the control, group B as the treatment or as the variation. So let's say group A are users who are exposed to our current design of the website or the ad, and group B are exposed to the variation we're considering, So the statistic that we're interested in is B minus A, the conversion rate in group B minus conversion rate in group A. So, we do the experiment and we measure the, behavior. So we have, let's say, 20 subjects, 10 of them belong to group A, the other 10 to group B. This assignment must be random. And then, let's say in group A, 4 of them converted, meaning clicked on the link. In group B, 7 of them clicked on the link. So the total number of converted is just adding these two numbers. The total number of not converted is total subject minus this. Percentage of conversion in group A is just number converted divided by total number of people in group A. Similarly for group B. Then the statistic that we are interested in is the difference between these two percentages. So in our example, 70% minus 40%. So here I'm just printing the result. So we already had this, it was, we provided it here, right, with these numbers. And the difference is 30%, but numerically Python shows it to me like this. It doesn't matter. So this is the observed difference. It is 30%. In total, we had 11 people who converted and 9 people who did not convert. So now I'm going to just put these 9 and 11 in a bag, right, and resample without replacement from that bag. I'm going to resample 10 and call that pretend group A, and the other 10 will be pretend group B. And I just do this resampling many times. So this is just one resampling. So I'm just, considering a bag of these results, something that looks like this. This is the bag. There are 11 people who converted, 9 people who didn't convert. That's the bag. Now I'm going to reshuffle the bag. I get something like this. This is the same list, but the entries are reshuffled. I have 11 ones and 9 zeros. Then I can say, all right, this part is A, and this part is B. Does it make sense? All right, now this is the resampled group A, and this is resampled group B. Now in the resampled group A, conversion rate is 50%, and here it is 60%. Therefore, the difference is 10%. So the resampled difference is 10%, and the observed difference is 30%. So just like what we had on this slide. Here, the observed difference was 30%, the resampled difference was 10%, and this is just one resampling. Now we're going to just repeat this many times. All right, so here I'm just repeating this resampling p times. So let's try 100 for p. It's just what we did in the previous chunk of code, but now based on p, I have a for loop for p, and I just reshuffle the bag and then consider the 10 items as A, the other 10 as B, and measure the resample difference. Then I append this resample difference in some list, and then get the mean and standard deviation of the numbers in that list. So the mean in that list is very close to 0, which means the center of our distribution is somewhere at 0, and the standard deviation is this. Then if we want to see the null distribution in a table, it's like this. We had 100 resampling. Out of those 100 times that we resampled 3 times, we got a statistic equal to 0.5, 50% difference. 18 times we got 0.3, 31 times we got 0.1. So there were just 6 possibilities, and we got those values with these frequencies. So these are just the raw frequencies. If we want to look at the same result but as a distribution, it looks like this. So these are the frequencies, right? So here we had 31. So the height of this bar is 31. And then on the y-axis, I'm representing the density of what we get from this histogram. So this is the null distribution. This is the null distribution. Now it's just a matter of how extreme this line is compared to this null distribution. This is the same null distribution, only the y-axis is stretched a bit. So stretched to, it's the same thing. Here you can see that it's around this. And now the question is, what is the area in here? That area is same thing as these values. The fraction, how large these values are. So for one-way test, cases where I got something equal or more extreme, it was 18 plus 3 divided by 100. That's for one-way test, right? So it's 0.21 or 21%. For two-way test, I should also include these observations. So for two-way test, we have these 2 numbers and these 2 numbers. So here are the p-values. So here I'm doing both two-way test and one-way test, but we need to decide, what hypothesis we are testing, and only do one of these. We cannot do both of them and see which one gives us, statistically significant results, and then decide. We should decide in advance what we want to measure, what we want to test. So for the two-way test, I'm looking at how many times the absolute value of these resampled observations are larger than the true observed value. For one-way test, I also consider the sign, right? So these are the 2 p-values. Oh, this is really slow. So the 2 p-values, disconnected. Let me try again. Okay, yeah. The two-way p-value is 41%. The one-way p-value is 21%. None of these is less than 5%. So we fail to reject the null hypothesis for both of these tests. All right, so what is the interpretation? Well, when p-value is larger than the predefined significance, which is usually like 5%, we fail to reject the null hypothesis, and the interpretation for a two-way A/B test is that the change does not lead to statistically significant difference, for better or worse. It means that there is no evidence of an effect. In the context of one-way test, where the null hypothesis is, let's say the null hypothesis is this, and then failing to reject means that changing from A to B does not lead to statistically significant increase. So now it is about whether there is meaningful increase or not in the outcome of interest, which in this case was conversion rate. It means that there is no evidence of an increase. So with two-way test, we're looking for evidence of effect. In one-way test, where null hypothesis looks like this, and we're changing from A to variation B, it's about whether we find evidence for an increase when we change from A to B or not. So this is when we don't have a discovery. This is when we fail to reject the null hypothesis. For the case where p-value is smaller than the threshold of statistical significance, we reject the null hypothesis. It means that we make a discovery. For two-way test, it means that we reject, for two-way test, it means that this change leads to a statistically significant difference. It also means that there is evidence of an effect. In one-way test, it means that rejection or discovery means that changing from A to B leads to a statistically significant increase in conversion rate. It means there is evidence of an increase. And one important consideration here is that absence of evidence is not evidence of absence. So sometimes we don't have evidence to reject the null hypothesis. It just means that we continue with our default assumption, but we cannot make conclusions from that. It happens quite often. People make this mistake of trying to conclude something from not observing something else. So one example that I can think of is receiving an email from some IT manager that there were no complaints about something, and implying that that idea is working perfectly. So when there is no complaint, it means that there is no evidence of something. And from lack of evidence, we cannot conclude anything. Of course, it's fine to go with the default assumption, but this doesn't imply that there is evidence of absence. It doesn't imply that something doesn't exist. So we can only make a claim or make a discovery when we have some evidence. So there is also a lack of symmetry here. It means that rejecting a test allows us to claim something. Failing to reject a test does not allow to claim anything. All right, so I guess we covered this part last week. So statistical significance does not determine the effect size. So it determines our confidence in what we claim to have discovered. Lack of statistical significance, which is the case of having a large p-value, means that we are not confident to claim that we have discovered something. And statistical significance does not translate to practical significance or practical relevance because effect sizes can be small. So I think we talked about this, that with sufficiently large sample size, when we're trying to measure difference between two samples, as that difference in the population is some value, and that value is unlikely to be 0 because it's just one value in the continuous range of numbers, it's impossible for that value, that unknown value, to be exactly 0. Therefore, with a sufficiently large sample, we can always reject null hypotheses. But sometimes these rejections are about just some tiny effect sizes, because the difference could be some tiny value that is very close to 0. But if our test is sensitive enough, we are able to also detect that tiny difference. And that tiny difference is perhaps not practically relevant. So if changing the color means that conversion rate changes from 20% to 20% plus 10 to the minus 10, we may be able to observe that when we're working for some large tech company where every second there are hundreds of thousands of users on their website, and we can measure them. We can measure their behavior. But whether we should change the color of the ad or not, that's another thing. That's not necessarily, that doesn't come automatically from result of a discovery. So experiments should be pre-registered to be meaningful. So for example, we cannot just run both of these at the same time and see, all right, this one is not less than 5, so let's forget about it. Just consider one-way test. We should pre-register that what we want to measure, all the experiment setup and everything. Otherwise, we are hacking the system. We are just p-hacking, right? Which is unfortunately a common practice, because when we fail to reject, we don't have anything to say. We don't have a story. And many people are in situations that they need to have a story, I guess, for their job. At least in academia, I guess many people feel that pressure. That's why there is a wrong practice of just doing more tests and making changes to the test so that eventually we have some story to tell. That story would not be meaningful, of course, because for one reason we have changed the test, and for another reason we have done multiple tests, right? So there's also a concept of power analysis, which is beyond this course, but there's a link to some discussion on power analysis that allows us to determine the sample size. So usually we determine the sample size based on the minimum effect size that we want to be able to measure, the probability of true positive, which is 1 minus beta, or power of the test, and significance threshold, which is our tolerance for false positive rate or type 1 error. So usually we have some values for these three, and based on these three values we decide what the sample size should be. And you can get more information from this link. Any questions? Well, we had just one example, right? But for doing the actual experimentation, I don't have like a website that I can actually, A test. Well, I don't have any examples, but the idea is repeating the same thing. Just we expose, the coding part is exactly the same. Only here, this group B is not really a different group. This is a different group, but also in that group, the subjects are exposed to the same thing that group A were exposed to.
So the answer will be the same.
Sorry?
A and B will be the same, so that their minus result will be 0.
So, well, we look at their conversions. If the samples are large values, the conversions would not be exactly the same. So in one group, let's say 300 people clicked on the link. In the other group, 310 people. The thing is, we should be able to, the thing is, for more than 95% of the cases, we should fail to reject for the experimentation to work. Because with AA tests, we know the ground truth. The ground truth is that the null hypothesis is true. Therefore, we should not be able to make too many discoveries. Yeah.
So we should do a test first, then we do
Yeah.
the test, right?
Yeah, definitely. To make sure that the randomization and other details of the test are set up properly. Yeah. Because there could be other things that cause some issues for the randomization. The random seed and everything. So maybe if you have like different servers, for your website, and then maybe some users from a specific geography, from a specific country, would be more likely to end up in group B. Something like that is concerning for a test. So for the randomization to be correct, every subject must have, I mean, in the case of 50-50 split, must have equal chance of ending up in any of the two groups. Yeah. We cannot reject the null hypothesis. So let me just go back to this. Yeah, for AA test, we should get p-values that are larger than 5%. Yeah, and we should get that for many tests. So we're going to do AA test many times, let's say 1,000 times. And in each AA test, we have like 100 or 1,000 permutations. Yeah. Our false positive rate should not be more than 5% because our tolerance for type 1 error is 5%. Yeah.
So for A test, we need to do like more than 1,000 times of the previous step.
Yeah.
And then we need to get 95% which are
Fail to reject. Yeah, 95 or more. Yeah.
then we can say that.
Yeah. Any other questions? All right, I think I covered everything. Yeah, let's take a quick break.